Okay, so today we're going to be talking about the effect of resistive forces on the velocity of particles. The main problem in this experiment, we are interested in analyzing resistive forces in different fluids. A resistive force is a force whose direction is opposite to the velocity of the object. Therefore, a fluid with a greater resistive force will cause objects to move slower. Our main problem was to discover whether water or isopropanol had a greater resistive force and understand the physics behind this discovery. The key difference between the two solutions that we chose was the density of each fluid. Density is defined as a measurement that compares the amount of matter an object has to its volume. The density of water is 997 kilograms per meters cubed, while the density of isopropanol alcohol is 786 kilograms per meters cubed. The main variable being analyzed, the velocity of particles in a fluid, can be derived by taking multiple data points of the particle's position as it moves throughout the fluid and using the equation average velocity equals displacement over change in time. As a result, we desired to calculate the average velocity of the metal ball bearings to determine whether more dense fluids have a greater resistive force on objects that move through it. Our hypothesis was that the metal ball bearings will have a faster average velocity in the isopropanol alcohol because the balls will have fewer molecules to collide with as it moves through the fluid. The alternative hypothesis was that the metal ball bearings will have a faster average velocity in the water. Our null hypothesis was that there will be no difference between the average velocity of the metal ball bearings and the isopropanol alcohol in water. Our brief results were that the metal ball bearings traveled faster through the isopropanol alcohol, thus indicating that water had a greater resistive force than the isopropanol alcohol. This was consistent with our model, and the results strengthened our hypothesis and scientific reasoning behind the phenomena.
Okay, so for our experimental design, we had metal ball bearings, a graduated cylinder, DI water, and isopropanol. We modified which liquid was in the cylinder as our independent variable. Our dependent variable was the velocity of the ball passing through it. Our controls were the same mass density, which was from the ball, same cylinder, same amount of liquid, and same method of data collection. Then we did a system schema relating the ball bearing, liquid, table, and the cylinder, and all the forces with that. We also did a said free body diagram relative showing the forces on the ball, resistive forces from the liquid, and the force of gravity. So our models for everyday life, we look like traffic. If you were to try to drive your motorcycle through image on the left, which we're representing as water, water is a lot more dense than isopropanol. You'd have a lot more tougher time passing through because there'd be more collisions, more interactions, whereas on the right hand side it's a lot easier because it's less dense. Obviously there's a difference in volume in this real life situation, but we're pretending that it's the density. In a computational context, we have the same thing, being the ball bearing is the green large molecule trying to pass through all these other ones. Water is going to be a lot more dense, so it's going to be a lot harder to pass through, whereas isopropanol is going to have a lot easier time.
In our results, we found that metal ball bearings and isopropanol had higher average velocities and peak velocities in both trials than in water. Furthermore, we believe the terminal velocity was not significant in this experiment because the graduated cylinders that the bearings were dropped in were not deep enough for the bearings to reach terminal velocity. We never saw acceleration as 0 in any of our trials.
So our equations variables, we related force of drag, drag coefficient, surface area, density, and velocity to find which one's better. Our average velocity from water was 3.9325 times 10 to the negative 3 meters per second, whereas isopropanol was approximately 5 times 10 to the negative 3 meters per second, so it went a lot faster in the alcohol. So we went through the calculations and found that the drag force of water was far greater than the drag force of isopropanol, and that greater density yielded greater drag force and a smaller velocity. Our limitations for this experiment is that we used our phones for videotaping, so limited frames. We were limited to the height of the graduated cylinder, so we couldn't reach terminal velocity, and acceleration never reached 0. We also didn't investigate the role of viscosity, which could play other factors into this experiment.